So all I want to do in this short little video is kind of catch up to where we were last time at the end of class, and then as a result of us not having class today, I ran out of time last time. I want to finish the derivation of the 3-point formulas that we were looking at for the derivatives. So this is where we left off. If you'll remember, we took a function f and wrote it as its Lagrange interpolating polynomial plus the error term, and then took the derivative of that function on this side and thus took the derivative of the interpolating polynomial here and then plugged in xj. And so when we take the derivative of the first Lagrange interpolating polynomial, this is what we get, and then we plug in xj in for the x right here. And this was the second one, this was the third one. And so what you have is f at x naught, and then 2xj minus x1 minus x2 over this denominator, and then these two terms very similar looking to that. And then this is what the error term turns out to be, because once we plug in xj, the extra error term that showed up whenever we had to do the product rule on the last term, very messy. There was even a third derivative involved. We didn't know what it looked like, but once we plug it in x sub j, and it would work for either x sub 0 or x sub 1 or x sub 2 into that formula, that last term just drops off. Okay, so again, we've got 3 points, x0, x1, and x2, and so what I want to look at is what does this formula turn into whenever you plug in, say, x0 specifically, or x1 specifically, or x2 specifically. And if you think about that, what that looks like on the x-axis is we're either plugging in a point and using that point, the next point, and the point after it, so a forward-looking formula to approximate the derivative, or we plug in x1 and we're using that point plus information behind it, information ahead of it, so this is like a central formula, and this one is going to be a backwards-looking or a backwards difference formula. Keep in mind the difference here is still h, so then we can let x1 be x naught plus h, and x2 is x naught plus 2h. So consider then what happens if we let xj be x0. So we're going to plug x0 in, and up here that means we get, and by the way, plug these in as well. So all of these turned out to be things that have h's in them. You get f prime of x0 is equal to, now if you plug in x0 in here, right, this term is going to stick around, so you're going to have f x naught, right, times 2x0 minus x0 minus h, because I'm subtracting it, minus x0 minus 2h, because I'm subtracting it. I'm just distributing the minus sign on this guy, over x naught minus x naught minus h times x naught minus x naught minus 2h. Just substituting those three things in. The next one would be f at x1. You have a 2x naught minus x naught minus x naught minus 2h divided by x naught plus h minus x naught, because x1 is x naught plus h, times x1, which is x naught plus h minus x naught minus 2h, plus 2, oh, and don't forget the f of x2 here. So 2x naught minus x naught minus x naught minus h divided by x naught plus 2h minus x naught times x naught plus 2h minus x naught minus h, and then plus still the error term, 1/6 f, the third derivative, c sub j. And I'm leaving off something, because I left something up here. This was times x minus x naught, x minus x1, x minus x 2 with a j plugged in on each of those. Right? No. When you plug that one in, one of those drops out. You end up with, actually, this is what I didn't finish last time. Just the error term up here. This is actually a little bit more complicated than I wanted to spend time talking about. What ends up happening is you have the product of the other two factors that don't include this one. So it's like from j equals 0, sorry, from k, let's say I, equals 0 to 2 of x j minus xi, where I is not equal to j. So what that means is that this term right here ends up having plus 1/6 the third derivative at c sub j times x0 minus x1, which is x naught minus h, times x0 minus x2, which is x0 minus 2h. Like that. That's times right there. Okay. So now we do some simplifying, because this x naught and x naught is gone. This is gone, and this is gone. And so you're left with a minus 3h, right? This is minus 3h over a 2h squared, right? So that gives me a minus 3/2 times h on bottom, so 3 over 2h times f of x naught plus, okay, this one, the x naught's again gone, so you get a minus 2h on top. Okay, this is gone, so that's h. This is gone, so that's minus h, right? So the minus over the minus cancel, the h over the h squared cancel, and what you're left with is just a 2 over h f of x1. And then this last one, 2x naught, x naught, x naught. You're left with a minus h on top. X naughts are gone here. These x naughts are gone, so you have 2h and that's just times h. So on top I have a minus h, and on bottom I have a 2h squared. So that should give me a minus 1 over 2h f at x2. Plus, now this one and this one, the x naughts are gone, this is gone, I get a minus 2h times an h, so positive h squared, sorry, 2h squared times this 1/6 means I've got an h squared over 3 times the third derivative at c, and this is no longer j, this is actually 0 because we're on the 0. Okay, so this again is what we get if we plug in x naught into the derivative of our interpolating polynomial with error term, having taken this derivative. Okay, it's more commonly written, by the way, this way. You pull out the 1 over h and do a negative 3/2 times f at x naught plus 2 f at x1 plus 1/3. This is not h squared. Sorry, this should have been 1 over 3. No, this was right, h squared. This was 1 over 2. Sorry, I got ahead of myself. Minus 1 over 2h f at x2 Okay, so here's your approximation formula for the derivative. This is a new way to approximate the derivative. If you have 3 points, a point and 2 more points equally spaced after it, this will give you an approximation of the derivative. Plus, you know by looking at this that it is a big O H squared convergence rate. Okay, that means it's better than the one we had yesterday. But this formula right here is what's called the forward difference. Okay, 3-point formula. Now I'm going to spare you going through the details of plugging in x1 and x2, but I do want to write down the formulas for you, what you get whenever you do the central difference and the backwards difference. So this formula right here you're going to use extensively in your homework. Another one that you're going to use would be if you wanted to do it at the midpoint and you had a previous point and a point after it. If you go through this process, you end up getting 1 over 2h times. Actually, I'm just going to leave 1 over h, so it's 1 over h on all 3 of these. And it's negative 1/2 f at your previous point. So evaluate to find the derivative here, evaluate the function before it, the function value before it, multiply that times negative 1/2, and then do the point after it. But there's actually not even an x1 in this formula. This right here is enough to do the central difference, plus your error term ends up looking like 1 over 6 with an h squared, the third derivative, and you can see 1. So again, this is also big O of h squared and order h squared over 6, which is something to notice. We'll talk about in just a second. This is actually half the error of the other one. If you do the derivative at the last point, you get a formula very similar to the forward difference formula. So this one right here I'd call the central difference. 3-point formula. Although technically it's only a 2-point formula because you only need x0 and x2 to plug it in. Okay, so the last one is 1 over h times 1/2 f at x0 minus 2 f at x1 plus 3/2 f at x2 . So if you want to know the derivative at the right-hand point, you can do the 2 points before it, and you get the same error term. Actually, it becomes a plus. This one was a minus. It doesn't really matter in the long and short of it, but this one becomes plus h squared over 3 f third derivative at c2. Also, we go h squared, but that would be the backwards difference. Okay, so there you go. I'm going to do one more board worth of work and then I'll be done. I want to use these formulas as an example so you can see how they actually work in practice. But you've got now 3 new formulas that are much more accurate in terms of converging to the derivative. We want to approximate the derivative when we don't know the formula for the function f. All right, so here's an example out of the textbook, one of the homework problems, similar to the type of problem you're going to be asked to do. Essentially what you're asked to do is we're going to come up with the derivative at each of these 4 points using the most accurate formula available. Okay, now there's a couple formulas that I didn't give you in the book that I would like you to at least look in the text and refer to. There are 5-point formulas for the approximation of the derivative. Now in this example, because there are only 4 points, you can't use the 5-point formula. So the best we could do is one of our 3-point formulas. When you're at a table like this and you have the first point, next point after that, next point after that, I want you to notice that they're all equally spaced. For the first one, you would have to use one of the endpoint formulas or the forward difference formula, right? This one, you have a choice of either doing the forward because you have this point and then 2 after it, so that's a 3-point option. But the more accurate formula, as I just told you, because the error was in half of the other 2, would be to use the midpoint or the central difference 3-point formula, which uses the point before it and the point after it. So I would use a different formula for the first one than I would for the second and third one. And then I got to go back and use the endpoint formula again, or the backwards difference in this case, for the last one to approximate what the derivative for each one of these would be. Okay, so I can find the derivative as accurately as my formulas will let me. If I have 5 points, that's when I would look up the 5-point formula in the book and use one of those. Okay, so for this 7.4, we're going to use the forward difference formula, the endpoint, or forward difference, which looks like this. F prime at x naught is 1 over h, okay, times, and I don't have these memorized and don't expect you to memorize them either, but it's negative 3 halves f at x naught plus 2 at f of x1 minus 1/2 at f of x2. So this is now 1 over, and h in this case is clearly 0.2 because that's the step size. 1 over 0.2 times negative 3 halves times negative 68.3193 plus 2 times negative 71 times 6982 minus 1/2 times negative 75.1576. And I'll go to my calculator. I'll probably cut this part out of the video and get straight to the answer, but negative 16.69325. All right, to do f prime at x1, I'm going to use the midpoint or central difference 3-point formula, which is 1 over h times negative 1/2 f at the point before it plus 1/2 f at the point after it. Okay, these are approximation, probably be clear about that. So that gives me 1 over 0.2 times negative 1/2 at negative 68.3193 plus 1/2 times negative 75.1576. Okay, so we're here and we're using the point before it and the point after it. So let's go to the calculator. Is a negative 17.09575. And I think you get the idea. This one's going to be the same exact formula, only I'll use this point and this point. So I'm going to skip over that. And let's do f of x, f prime at x3. Just kind of see how I adapt the formula. Remember that the formula was something to the effect of a positive 1/2, a minus 2, and a positive 3/2. But it was, if I'm going to do from x3 or from this 8.0, I'm going to do that point in the previous 2. And so I start here and work my way towards this one. So it's still 1 over 0.2. It's going to be, it's 1/2 times f at 2 points before this. So f at x1 minus 2 at f of x2 plus 3/2 at f of x3, where I am. Okay, so 1 over 0.2 times 1/2 times negative 71.6982 minus 2 times negative 75.1576 plus 3 halves times negative 78.6974. And to the calculator, negative 17.9. And again, the only reason I left this one out is because the process is the same as this one, so you should be able to do this one with these 2 points. But that's how we would do a problem where we use our best formulas. Now, some of the other problems will involve using your error terms, and you can certainly come ask me some of those questions, maybe even ask me in class, and I'll talk a little bit about them there. But that's all I wanted to show you for today, and now you can go ahead and start the homework for 4.1.